So we're going to talk about other coordinate systems. What we talked about so far is just using rectangular coordinate system, rectangular coordinate system, which is just x, y, and z. Any point in the space is denoted by x, y, and z. X, comma, y, comma, z. Well, we can introduce a new coordinate system that you saw before using polar coordinates, but in the space, in 3D space, we call it cylindrical coordinate system. So cylindrical coordinate system. Coordinate system. We say that, hey, suppose you have a surface in cylindrical shape, then in that case, we define x to be r cosine theta, y is r sine theta, and z is equal to z. This is called cylindrical coordinate system. So if we have a larger cylinder, that cylinder behaves like this. So suppose you have this cylinder, and then you have an object moving along this cylinder. Well, suppose that point is just right here. This is a point that has x, y, and z. You can convert x, y, and z using r cosine theta, r sine theta, and z equal to z. Z stays the same. If you look at the projection of this point in x, y plane, this guy doesn't have any z anymore. At this point, it is just x and y. And since the base is in a circular shape, let me graph this here, the base in circular shape, then you have your x-axis, you have your y-axis. Well, this point x and y is, for example, right here. We all know that we can use r and theta in polar form and convert the whole thing. X is r cosine theta and y is r sine theta. And as we move this point above, it means that we're taking this and moving it to the higher place or lower place with the distance, which is just z. Now, we say that, well, we have the third coordinate system, which we call spherical coordinate system. It has more variables. So spherical coordinates. In the spherical coordinate system, we say that, hey, our object is moving along a sphere. Okay. Let us have a huge sphere here. And our guy is moving along this sphere. I have my x, y, and z-axis. And my z-axis are right above here. So you have your particle. Instead of moving on a cylindrical shape or just randomly in the space, it behaves the way that it moves along a sphere. Suppose that point is just right here, x, y, and z. We can define the distance between this point and the origin. The distance is just right here. We call this distance rho, and we say that rho is equal to square root of x squared plus y squared plus z squared. This is our rho. Well, this point forms an angle with the positive part of z-axis. We're going to call that phi. This is my phi. This angle is called phi. So phi is the angle with the positive part of z-axis. Well, okay. If I look at the projection of this point in xy plane, I'm going to get something like this, right? So the projection of this point in xy plane. Suppose this guy is just right here, the projection. At this point, you don't have any z anymore. You only have x and y. Z is equal to 0. So here you have your x comma y, x comma y. Well, like before, you're going to have a distance in xy plane, right? In xy plane, this is your r. As before, the angle between your point with the positive side of x-axis is called theta. Everything is the same as before. So x is r cosine theta and y is r sine theta. But here we can find the relation between r and rho. How? Using the definition of sine and cosine. Well, okay, we're going to have the exact same distance here. These are two parallel lines. R. Sine of phi is defined as r divided by rho. So r is rho sine phi. Wherever you see r, you can plug that, you can substitute that by rho sine phi. So now x is rho sine phi cosine theta and y is rho sine phi sine theta and z is equal to rho cosine phi. So if we write the definition of cosine, you're going to see this length is just rho cosine. Rho cosine phi. Just an important note, this new angle, it can only range between 0 and pi. It doesn't rotate completely. Your phi is always between 0 and 5. When you're talking about spherical coordinate system, this is an important note. Your phi cannot rotate fully. Your phi starts from North Pole and stops at South Pole. It doesn't go around. In cylindrical coordinate system, what are you going to have? You're going to have your point P, X, Y, Z in the space. If you look at the projection of P in XY plane, you're going to use the polar coordinates that you used before, r cosine theta and r sine theta for your X and Y. Well, so this is my point. The point is moving in the space. If that point is exactly on XY plane, it means that my Z is equal to 0, right? So this guy shows that Z is equal to 0. It means that, well, I only have this point in XY plane. I can change the radius. The radius is getting smaller, getting larger, and your theta, your angle, rotates 0 to 2 pi because you have information in XY plane. As I move this point above the z-axis, the z value gets larger and larger. I can change this angle, and this is the behavior of this object. This object is moving in the space on a cylindrical surface. This is your particle. Again, your radius can be changing. Your theta is changing. And then your z is changing, of course. This object can be above or below z. Its height is changing. In this new system, spherical coordinate system, you have the object. This is the point in the space. Well, this is in the space, and then this guy is moving along a sphere. Last time we had a cylinder, now we have a sphere in the space. These are the conversion that we have when our object is moving along a spherical surface. If you look at the projection of your point in XY plane, you're going to have the regular conversion for r sine theta or cosine theta in XY plane. But in spherical coordinate system, we define rho, which is the distance between the point and the origin, and also we define this new angle that the object creates with the positive side of z-axis. Well, by using the definition of sine and cosine, we can get these two measurements, these two distances. Remember that in XY plane, you have r using phi and rho. We can convert that into rho sine theta and the rest of the conversion. X is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho sine phi. This guy is called phi. So let us take a look at the behavior of this particle as it moves along a spherical shape. Well, this is my object. It's just moving along to all the directions. But note that the behavior, it's not like before. It's not the cylindrical behavior. It can just go to the left, to the right, and it changes the distance. Rho, the distance between the object and the origin, is changing. Theta is the angle that it creates with positive part of x-axis as before. And phi is the new angle that we introduced. Phi is equal to 0. It means that your object is exactly on positive part of the axis. As we move along, phi increases. It means that your object starts falling down. But at most, it stops at the South Pole. It cannot go to the other part. It just have half rotation. It doesn't have a full rotation. Phi is bounded between 0 and pi. Very well. Give us examples. Sure. Let us go over a couple of examples, see what's happening here. Let me write them down so you know what's going on. XYZ can be written as in cylindrical X r cosine theta, Y r sine theta, and Z equal to Z. And then in spherical, you have the following. Question. convert this point to -2 square root of 3 and 3 to spherical. Convert point P to -2 square root of 3 and 3 to cylindrical and spherical coordinates. What's the conversion? If you want to convert this into cylindrical form, what do we have? What about your spherical coordinate? What is your x? What is your y? What is your z? What is your x? What is your y? What is your z? Very good. So remember that to convert our point, we have our x, we have our y, we have our z, x, y, and z. In cylindrical form, we don't have any problem with z. Z is equal to z, so you're going to copy down z as 3. Z is 3. But what is x? X is r cosine theta. What is y? Y is r sine theta. But how do we calculate r? R is equal to square root of x squared plus y squared, and theta is equal to inverse tangent of y divided by x. So my r is equal to square root of, what is my x? X is 2, so you get 4, plus, what is your y? 2, 4 times 3, which is 12. So you get square root of 16, which is 4. This is my r. So far I have 4 cosine theta, I have 4 sine theta. But what is theta? Theta is inverse tangent of y divided by x. -2 square root of 3 divided by 2, which is inverse tangent of negative square root of 3, which is 5 pi over 3. So what I have so far, I have r, which is 4 cosine of 5 pi over 3 and sine of 5 pi over 3. Then we continue doing the calculation. So we get 4 times, very well, a half, and here we have 4 times negative square root of 3 divided by 2. So my x is equal to 2. My y is equal to, if you simplify this, -2 square root of 3. This is what we have here. You can just use that to make sure the conversion is correct. -2 square root of 3, and then here you have your z, which is equal to 3. Going back and forth between all of the information that we have and converting them into r and theta. So r is equal to 4 and theta is equal to 5 pi over 3. So in your cylindrical coordinate system, you're going to have r, theta, and z denoted as, so this is 5 pi over 3. You're going to have r, which is 4. You're going to have your theta, 5 pi over 3, and you're going to have your z, which is just 3. This is the conversion to cylindrical coordinates. So if somebody asks you, what is this point? 2, -2 square root of 3, and 3, In cylindrical form, you have 4, 5 pi over 3, and 3. Very good. So remember that here, this point x is positive and y is negative. It means that you are in the 4th quadrant, and using the equation to solve an angle, tangent of theta is equal to y divided by x, which is negative square root of 3. And using trig equations and going back to unit circle, you need to memorize some of the important angles. The angle is 5 pi over 3. Well, how do we convert that into spherical coordinates? In spherical coordinates, we have rho, which is equal to square root of x squared plus y squared plus z squared. So this is my rho. Rho is not very hard to calculate. X squared, 4 plus y squared, 12 plus 9. So my rho is equal to, well, I have 16 plus 9, 25. So my rho is equal to just 5. I found rho. The next step is to find x. X is equal to, well, I have rho, which is 5. I just found rho, and sine 5, cosine theta. I already found theta. I'm not really worried about theta. Sine 5 and cosine of 5. Pi divided by 3. And my y is 5 sine 5 pi over 3. If you write it this way, then the calculation on the right-hand side, the calculation on the left-hand side, they are all equal to each other. Well, what you can do, you can say that, hey, my z is equal to, you can use one of these equations. The last one is an easy equation to use. My z is equal to, we know that z is equal to rho cosine of 5. What is z? Z is equal to 3. 3 is equal to, what is rho? We calculate rho to be 5 times cosine 5. So that's how you can find cosine of 5, which is 3 over 5. And you can find phi, which is inverse cosine of 3 over 5. You have to use a calculator for that. Or you can leave it as 3 over 5. So this is my phi. Now that I have my phi, I use a calculator to evaluate this. Calculator. And you can substitute that number here. So if we use a calculator, our phi is roughly 0.93. 0.93, okay. 0.93, roughly. It gives me a rough value. Very well, if I plug those in, then I get x to be 2 and y negative 2 square root of 3. So, well, the point in spherical coordinate is rho, theta, and phi. Rho, theta, and phi is equal to 5 pi over 3. And inverse cosine, if you want to make sure it is exact, you need to copy down inverse cosine 3 over 5. But if you do the calculation, you get 0.93. So you can write down 0.93. This is your point in spherical coordinate. Very well. Give us an example.